都看得到吗？
可以，
闪在黑板嘞，
可以啊，
真的假的？
对，
这样对不对？
从那边到那里。
这么厉害 ？OK， 那大家都好了吗？
好了。
All right, welcome back to the class. So very quick recap of what we covered on Monday. We introduced electric field intensity. So later on in this class, it will be represented by this capitalized E and having a vector sign. So it is a vector field. What we covered was the two fundamental postulates. The first one is divergence of E is equal to the value charge density divided by the vacuum permittivity. All right? So this is telling you if you have some kind of charge distribution in space, it will set up its own unique electric field intensity pattern. Just like what I'm showing you at the bottom. So if we have a positive charge, by the divergence relation, we know that divergence gives you outward flux of the field. So in this case, all the E fields, they have lines. Okay, so these are called E field lines. They are radiant, just like sunshine. Okay. And the second postulate is telling you nothing more, but it's further enhancing this picture. So your E field for a single charge is radiant, and therefore the field being created by these charges will be conserved. Now, if you have a conserved field, then curl of this field will be 0, meaning it's conserved. Okay, you cannot gain work by walking in this field in a closed loop. All right? Okay, so let's continue. Based on our understanding of these two fundamental postulates, we are going to introduce Coulomb's law. Coulomb's law is derived from a series of experimental data. So more than 100 years ago, people performed experiments, and based on their experimental result, they were able to come up with some equation, a law, to find out what is the quantity of the E field intensity for a given charge. So that's really remarkable, more than 100 years ago. So using Coulomb's law, I'm going to explain, and we can really now quantify the E field of a point charge. Up to now, we only have a qualitative description. And we don't really yet know what is the real value of the E field in space. Okay, so we're using Coulomb's law. And after we search the E field at the point charge, I'll give you the definition of Coulomb's law. Then we can use Coulomb's law to find the field distribution for some charge variation. Okay, so we are based on a point charge, and gradually we expand to some charge distributions. Right? Okay, this is pretty much what I drew on the blackboard. We have a single charge positioned in space. Don't ask me how the charge came here, okay? That's out of the question. So assume, magically, we have a charge sitting in space. We can just use its position, and we define it as the origin. Okay? Now, I have an observer like myself, I am standing some distance away from the charge. And from the first postulate, I know that if I have a charge, it emits radiant field lines. So basically, the field profile will be most resembled by a sphere. Okay, so if you have a given single charge, the emission pattern of the field is like a sphere. So before we start, this is something we also derived, right? Starting from the differential equation, we expand it into the integration form. So this is what we have. So this is telling you, if I have a given charge, then I know its field distribution as long as I know where the observer is. Right? So in this case, how to apply this equation? This is telling you, if I am standing here, right, some distance away from the charge, I know the charge is giving a spherical charge field distribution, and I know my distance. So basically, I'm asking, when I change my distance to the charge, how is the field intensity going to change? I want to know the relationship of the field strength, its magnitude. So how does that relate to this equation? The distance between me and the charge is described by this differential surface. Or in other words, when I'm away from the charge, the sphere is getting bigger, right? The radius is getting bigger, therefore, the entire volume, the surface, is getting bigger. So therefore, for a given point, like my eyes, a given point, the field strength would certainly change as a function of the distance from myself to the point charge. All right? Okay, so now we know the essence, the meaning for this equation in integral form. Even though the charge remains unchanged, the field intensity, strength, its amplitude will change as a function of the distance from myself, an observer, to the point charge, right? So this E must be a function of distance. And that's what we're going to find out. And in doing so, we can quantify the field intensity, right? So how do we do that? So later on in this course, for the entire semester, the first thing you need to understand is, well, we spend so much time in learning about orthogonal coordinate systems. So the very first issue is, once you have a given problem, it has certain geometry. You need to find a proper coordinate system that is most convenient for your later analysis. Otherwise, why do we spend time in learning 3 different orthogonal systems? So in this case, we want to choose a proper coordinate system. And in this case, as we described according to our anticipation, single charge emits like a sunlight, right? So basically, your structure, the field structure, the dependence to distance, would most be resembled by a sphere. So in this case, we would prefer to choose spherical coordinate system. to work with. But again, spherical coordinate system is giving you the most complication because you have theta, you have phi, so you have two angular unit directions, unit vectors. So you have basically two arcs, all right? So I'm going to walk you through, although I bet all of you know the surface area for a sphere is 4 pi r squared. That is known from high school, but let me just walk you through and re-emphasizing why I highlighted on differential length, differential surfaces so much. All right, so we are going to work in the spherical coordinate system. The first thing, to use this equation, you need to be able to formulate differential surface. And in this case, if I have an observer here, the differential surface is pointing in which direction? In the radial direction. So this ds, the differential surface, is a vector. It should be pointing in the radial direction. So once the direction is in the radial direction, its area must be determined by the differential length of the other two unit vectors, dl theta and dl phi. So dl theta, ask yourselves, what is dl theta for spherical coordinate system? It will be an arc. So for an arc, you need to know the radius. So for dl theta, the entire radius is used to span the arc. So it is basically r d theta. But in the phi direction, not the entire r is used to span the arc. It's only r sine theta. Okay? So for dl phi, again, I'm repeating this just to emphasize the importance of your clear understanding to differential length and differential surfaces. So dsr, pointing in the radial direction, its magnitude will be determined by these two differential lengths in the theta direction and in the phi direction. So now we know how to properly address ds for the single charge. We put it in. So the closed surface integration of E field intensity, this is to be determined. We are trying to calculate this. But the knowledge is the radiating field will be uniform in each direction. So basically, if we perform a closed loop integration, we know the total field strength. Okay? Now, this E, because ds is pointing in the radial direction for a dot product to be non-zero, in this case, the E field intensity is also pointing everywhere in the r direction. And that conforms to our assumption, right? For a single charge, the field lines are all radiant. For each line is pointing in the radial direction. And that's the reason why I'm using ER. The E field intensity for a single charge is everywhere radial. So I'm having the direction, I'm having its magnitude. To properly integrate over the entire spherical surface, phi, the integrand for phi is from 0 to 2 pi, right? 360 degrees. But for theta, in spherical coordinate system, theta is the angle of your radius to your z-axis. So basically, theta only spans from 0 all the way to pi. So theta, the integrand for theta is 0 to pi. right? Now we look at the things inside. AR.AR is just, right, just 1. So there is no phi inside. So basically, d phi over the area, over the range of 0 to 2 pi is just 2 pi multiplied directly. Okay. So what we're left with is sine theta, d theta, integrated over 0 to pi. And that you know how to do. So I'm just showing you the result. So this is telling you 4 pi r squared is something we're very familiar with. It's just the surface area of a sphere with a radius of r. And that r here means the distance from the observer to the charge. So this is telling you the E field intensity amplitude is indeed related spatially, right? It is distance dependent. And that is equal to the charge contained divided by the constant. So through this simple example, I'm showing you, based on the knowledge of the E field intensity distribution being radiant, and it's conserved, we now finally know the E field intensity of a single charge with a very nice and precise quantitative description. So the field strength created by a single charge is inversely proportional to the square of the distance. Okay? Exact quantity would be having a charge divided by the square of the distance, and then divided by 4 pi epsilon 0. So this 4 pi r squared is coming from the surface area of the sphere. Right? This is nothing new. I believe each and every one of you learned about the quantitative measure of a single charge. Right? So this is nothing new. This is only to refresh your memory, and I'm using this example to highlight the importance of being able to use a preferred orthogonal coordinate system for this equation. Right? Now let's continue. You might be wondering, how can I just assume the E field intensity is pointing outwards? Well, if I'm drawing this E field intensity, all these field lines pointing outward, I am making another assumption. This charge would be positive, right? Like on the blackboard. If I have a positive charge, I have fields emitted outwards. But on the other hand, if the charge is negative, then all these field line directions would reverse sign. Is that fact captured or allowed through our derivation? If I change the sign of charge, so now Q is negative, then this AR is also changed to a negative sign. All right, so this included in my derivation. So this derivation result is valid. So if you flip the sign of the charge, the field flips sign as well. Okay, so now we're ready to define Coulomb's law. Coulomb, in fact, he measured the forces between two charged particles more than 100 years ago. It's very impressive. So he was asking the question, okay, if I have the first charge, Q1, right? The first charge is going to create its E field intensity distribution, like the one we just derived, Q divided by 4 pi epsilon 0 r squared. So he was asking the question, what happens if I bring a second charged particle, having charge Q2, and I allow it to sit somewhere, right? So the distance between the two charges is R12. In this case, what will be the resulting force experienced by the second charge? So his philosophy was, initially, you do not have the second charge, you only have the first charge. So the first charge, its function is to set up some kind of field distribution. And then somehow I bring the second charge, right, from very far away, and I just let it go. So the second charge also sits here magically. Don't ask me why, okay? Because under static assumption, nothing moves, okay? So basically, these two charges are very well behaved. They don't move. They have a constant distance of R12. And he performed experiments to measure this force by changing the distance, by changing the charge amount. So he came up with this nice equation. Force 12. Listen carefully how F12 is defined. Having the subscript of 1, 2 means 1, charge number 1 is setting up its field distribution to give a force on charge number 2. So E12 means the first charge is accounted for the field distribution. And this 2 is only to give the charge. Okay? So this means when you write F12, you understand about charge 1 is setting up the field distribution. Charge 2 is only trying to contribute this amount of charge. But you know the answer already, because E12 is already derived in the previous part point, right? It's just Q1 divided by 4 pi epsilon 0 R12 squared, right? This is E12, the field distribution created by the first charge. Because charge number 2 is seated R12 distance away from charge number 1. So this is where you put R12 squared. And that E12 is now multiplied by Q2. So this is Coulomb's law. In the same, if you have two charged particles, then they each exert some kind of force on each other. So the force felt by charge number 2 due to the presence of field created by charge number 1 is F12 will be this amount, this quantity. But at the same time, charge number 2 also creates its own field intensity pattern, and that field could also exert a force onto charge number 1, right? It's just a role reversed. You can imagine initially you have Q2 in space only, then you bring charge number 1 to the location. Exactly the same, it's just reversed. So in this case, Coulomb formulated the force felt by charge number 1 due to the presence of field created by the second charge will be having the same amount. They have the same magnitude, but the only difference is now the unit direction is reversed. Okay? So if these two charges are both positive, then E12 is pointing from 1 to 2. E21 is pointing from Q2 to Q1, so it's reversed. So this is really, again, nothing new. But what I'm trying to say is, Coulomb's law is really the direct analogy of Newton's law of universal gravitation. So now try to refresh your memory. You must be scratching your heads. What is Newton's law of universal gravitation? F is equal to m1 m2 r squared, right? You might have some coefficient, so then just write proportional. They are basically the same, right? So if you have two particles having their masses, they somehow have gravitational force. And that gravitational force is also inversely proportional to the square of the distance, but now you have m1 times m2. Right? So in that sense, Coulomb's law is a cousin or a brother of Newton's law of universal gravitation. But think more carefully. You have to be extremely careful and sensitive. In terms of amplitudes, Coulomb's law is identical to Newton's law. But they are dramatically different in one special aspect. And what is that? Well, in our daily lives, masses are always positive, right? So think about it. The dramatic difference between the two laws comes in the fact that charges are allowed easily to have different signs, positive charge or negative charge. But for masses, I mean, to the world that we're living in, masses are positive. So basically, for Newton's law of universal gravitation, if you have two masses, they always attract each other, right? But for Coulomb's law, if these two charges are having the same sign, the forces are used to repel each other. And if the two charges are having opposite signs, the forces are used to attract them together. So at this time, you must understand what I mentioned. Static electric field, everything you study here is fake, right? I mean, how can you have two charges sitting there without moving? It's impossible. Coulomb's law tells you there are forces between the two charges, right? Once they have the force, they would be used to expel each other or attract to each other. So charges would start moving. So in the real world, things become complicated. But here in the classroom, in for your understanding purpose, we make the assumption everything is being stationary, nothing is moving. So that is a super strong assumption, right? Now, what happens when the charge distribution is becoming more complicated and even continuous? In the previous case, we only considered two discrete charges. You can easily write your formulation. But what happens if your charge distribution is you have lots and lots of charges, eventually it becomes continuous distribution. Don't worry, it's okay, because basically the first postulate, divergence of E is equal to rho divided by epsilon. It's a linear equation. So all you have to do is add. So assume in space you have charge distribution 1, which is giving you E field intensity number 1, but nearby you have a second charge distribution is generating its own field pattern. Now you mix the two together. You put the two into the same box. What is going to happen? Well, math tells you it is linear, so you can add them together in any proportions. C1, C2 is just a coefficient. Okay. So if you mix these two together in any ratio, it's okay. All you have to do is, well, E1 and E2 is multiplied by the corresponding same ratios. Right? So there's nothing to fear. Coulomb's law tells us once we know the force between the two charges, we have more charges, we just add them all up. Okay? Because we have a linear relationship. So later on, we are going to investigate into two particular cases. The first one is if we have multiple discrete charges. So we might have 5 charges, but each one is a discrete entity, a discrete particle having certain charges. So that's case number 1. Case number 2, what happens if the charge is really continuous? Are we capable of finding the resulting field distribution? So let's wait and see. Okay, first case. We have discrete charges. So we have lots and lots of charged particles. Each one is having its own coordinate position. Okay. So I'm going to explain the nomenclature, mathematical terms I'm using here. I now have an observation point, so I want to know what is the total E field strength and direction at this P point. So this is my observer. I'm standing here. I want to measure the E field intensity here at this location. So that is, I need to know the position, right, for this observation point. And that position is itself a vector, r, right? I'm using r to express as a generic position. It can be x, y, z, can be r phi theta, r phi z, or r theta phi. Doesn't matter. So this r stands for my position vector of my observation point. On the other hand, I have lots and lots of charges. So Qk means the kth charge. For the kth charge, it has this quantity. Qk means the charge, the amount of charge for my kth particle. The charge has its own position in space. Now, to differentiate these two, the charge, I'm trying to differentiate the charge position from the observation point. I'm using the prime system. So this RK prime, so once you see it, you know, oh, this is mentioning about the position of the K charge, because you're having this prime here. Okay? So I'm using the prime coordinate to denote it is representing a source, a charge. The unprimed system is used to express the observation point. Okay, so this is my charge. For example, this is my first charge, and this is my observation point. I know the positions of both. Then I should be capable of knowing the distance between these two, right? The distance between these 2 points should be r, the observation position vector, minus the position vector of my k charge. R minus rk prime, and then I add the absolute value. That's the distance. For your reference, I'm showing you here this rk vector is r minus rk prime, both vectors. So the unit vector is the vector itself divided by its amplitude. This amplitude is r vector minus rk prime vector absolute value. Okay? So this drawing for only one charge, but that charge might be the 99th charge in space. With that knowledge, I can quickly write down, well, if I have n charges, each one of them is dispersed in space. So each one of them has its own position vector, but that's okay. All I have to do is add them up. And remember, this ARK unit vector is different for each charge. Why? Because each charge is having its own position vector. So basically, its RK is different for each charge. So the direction and magnitude are different for each charge. So all I have to do is add them up based on my understanding to Coulomb's law. Right? Each one of them is setting up its own E field intensity, which is inversely proportional to the distance from the charge to the observer. And the direction is defined by the unit vector and the sign of the charge. Now, the second expression, I want to replace the unit vector by this expression, highlighted in yellow box. Okay. They are the same thing. It's a different way, just explicitly writing out the unit vector. So all I have to do is add them all up. Straightforward and easy, but now let's look at a real, well, example. So example is, well, you have all these derivations in front of you, but my recommendation is they are extremely easy, but try to work on your own. Just cover the answers and try to work on your own. Now I'm only having two charges, Q1 and Q2. The first charge is having 2 coulombs, and it is seated at a position in the Cartesian coordinate 1, 0, 0. The second charged particle carries a negative 3 coulombs, and it is situated at 0, 1, 1 position. And the question wants you to answer, what is the net, the total field intensity at an observation point of 1, 1, 0. This is like going back to high school, right? The main point is whether you're able or not to calculate vector analysis. Okay? So try to work on your own. I will explain it slowly. And when I finish, you can compare your result to my result. Okay, we know the observation point. We know its vector, 1, 1, 0. We know the position vectors for the two charges. So the first thing is the R1. The R1 vector is my observation position vector minus my first charge position vector. So this is 1, 1, 0 minus 1, 0, 0, so it's 0, 1, 0. So its amplitude is just 1. Okay, R1 is 1, so you know this R1 is 1. I could repeat the same procedure for the second charge. R2 vector is my observation position vector minus the second charge position vector. So now it's 1, 0, negative 1. So in this case, the distance from the observation point to the second charge is square root of 2. Okay? Now, once you know this, so this is the vector and this is the amplitude, you basically know everything. So all you have to do is invoke this equation and you sum them all up for the two charges. K equals to 1 to 2. You only have two charges. You're lucky. But I can guarantee you during examination, I won't be so nice. At least 3 charges. Then you're going to hate me. Now you like it. All right, so basically just add them all up. Don't ever forget the charges comes with a sign. The second charge is carrying a negative 3 coulombs. Okay, so this is why you have negative 3. Basically just add them all up. So a very simple problem, but it's really testing on your ability to perform vector adding, subtraction. That's it, right? Such a simple problem gives you this complicated answer. So how many of you are getting the same result as I am? I hope I'm right, okay? All right, so take a look. I'm not teaching you a lot of stuff. I'm merely showing you. Once we follow Coulomb's law and we know how to properly formulate the E field intensity of a single charge in a quantitative sense. Quantitative means I know its magnitude, I know its direction. And that's extremely helpful because once we know the E field for a single charge, we can extend it into charge distributions. So this example shows you I have multiple discrete charges. And next one, I'm going to show you what happens if I have the two charges, but in a very unique way. Okay? In this case, it's called an electric dipole. It's a very fundamental building block to our understandings, to the world of electromagnetic waves. So later on, I will come back to electric dipole multiple times. So electric dipole is arranged uniquely. You have two charges separated by a distance of d. So this position vector is defined from the negative charge to the positive charge. So these two charges have the same amount of charge, but they have opposite signs. Okay? So this is positive Q, this is negative Q. And by convention, the position vector is defined from the negative charge pointing to the positive charge. So this D itself is a vector. Okay? All right, so let's try to extend what we know already. Directly, I can just write down the total field intensity due to these two charges. One is positive, one is negative, right? I have an observer, so the observation position is r vector. These two charges have their own distance vectors relatively to my observation point. So for the positive charge, this is r vector minus d divided by 2. For the negative charge, it's r plus d divided by 2. So we have a total of 3 position vectors, right? And that's the reason why you have this result. Okay, so this is straightforward. I mean, once you understand Coulomb's law, you can write down the field expression directly. But what is more interesting is what happens if the observation point, this r, this distance, the magnitude of r position vector is far, far larger than d, meaning we're very far away from this dipose. What happens? So this is a mathematical trick. So this blue part, 1 over r vector minus b vector divided by 2 cubed. I want to find some approximation, right? So this magnitude negatively cubed means this 1 over this. Okay. So that is equal to the square and take the square root. This is purely math. You multiply everything out, you have this 3 contributions. And now we want to make approximations, and usually by knowing that we are very far away from the dipose, so this r magnitude is much, much larger than the d magnitude. So which one of the 3 terms can be canceled out or ignored? The last term, right? R squared as compared to d squared is very big. So you have a very small value divided by a very large value. This one can be ignored. Then you know this first item, 1 over this blue part, can be approximated by this expression. By the same analogy, the red part can be approximated by this value. So you have all this in front of you, so I can go slightly quicker. What I want to tell you is having this expression helps a lot to our understanding to the voltage we're going to introduce later. Okay. So up to now, I'm showing you this is one example again to use Coulomb's law for discrete charges. But when you are far away from the charges, you can further make assumptions and simplify your result. But let me just stop here for this case. I will come back to it. Okay, when the time approaches, I'm going to notify you this. But for the very last 2 minutes, I promised you Coulomb's law can be applied to having multiple discrete charges and even a continuous charge distribution. So if in this structure I have lots and lots of charges, can I still try to find out the resulting E field intensity pattern? Yes. So in this case, all you have to do is each differential portion will contribute to a part of the total E field intensity. So all you have to do is perform integration. So once you have a continuous distribution, instead of having summation, Summation is for discrete charge distribution. When you have continuous distribution, you use integration. So if your charges are distributed in a three-dimensional volume matrix way, you have a volume integration. If your charges are dispersed in a surface aspect, you perform surface integration. And if you have a line-like distribution, you just integrate using line integration, right? Next Monday, according to the schedule for the university, we have no classes. So we will come back to this one next Wednesday. And so enjoy your long holiday. But before we close, we have decided the first examination will be taken on April 20th, which is a Monday. During class time, okay, during class time. So you will receive an email from the head TA, Ms. Wu, telling you the specific directions. We don't want you to come into the classroom due to the virus, okay? So we have figured out the best way to conduct the examination. So try to be sensitive, and once the TA sends you the email, I will notify you again. I will warn you again. So we will have a practice session to make sure everybody can perform the examination on your own. All right, so just wait for the email. All right, see you next Wednesday.